have junior faculty speakers with the goal of getting them to be introduced to our wonderful students here, as well as to our wonderful senior faculty. And so we'll have Anil Damle from CS is going to give the first talk for about 15 minutes, and then we'll have Moghadam from MAE and Nikolaos Bouklas also from MAE.
Cool. All right. Thank you, Austin. I guess thank you all for coming here and for enjoying this. Hopefully you'll find this Colloquium enjoyable. So what I'm going to talk about today is a little bit of invariant subspace perturbation theory and applications in abridged form. So there's going to be just a few technical points, and then kind of the mid part of this talk, I'm going to use this technical work as a framing to briefly talk about a few of the other things I worked on. Some of you saw I gave a Colloquium last fall. You'll see like 2 shared pictures from that. So when you see those 2 pictures, you may recognize them before. Many of you are new. You will not have seen those pictures before, so they'll be new and exciting, perhaps. Okay, so first order of business, acknowledgments and then collaborators for this talk. So the bulk of stuff I'm going to talk about today is joint work with Yukai Sun at the University of Michigan in the statistics department. If you happen to be around, he actually gave the Scientific Computing and Numerics seminar talk last Monday, Monday of this week. And then when I talk about some of the application area problems we're interested in, that's joint work with Victor Minden, who's at Google now, Lexington Yang at Stanford, and Lin Lin at UC Berkeley. Funding for various parts of this has come from the NSF and DOE. Okay, so I'm actually going to start with a somewhat technical slide, but it's also a little simple and lets me frame things nicely. And that's to give kind of the mathematical crux of today's talk, and I think one of the, hopefully, a simple and understandable way. Okay, so let me talk through this. So the crux of today's talk is that let's assume I have some symmetric matrix A. Okay, this can come from any number of different applications. I'll talk about a few examples later on. But let's say I have a symmetric matrix A, and I have some matrix E I'm going to think of as perturbing A. Okay? So I have a matrix, comes from an application, but maybe I don't know what this matrix is exactly, and so I imagine that the matrix I actually have is some ground truth plus perturbation. Maybe I have a problem where I make measurements with random noise added to them, and I would like to understand something about this matrix. So I have a matrix A and I have a perturbation E, and I'm going to call A hat A plus E. Okay?
E is also symmetric?
E is also symmetric, sorry. Yeah, symmetric matrices A and perturbation E. Thank you. And just for some notation, we'll show up again later in the talk, I'm going to assume that A has eigenvalues lambda 1, lambda 2 to lambda n. And I'm going to assume lambda 1 is bigger than lambda 2. And these are ordered algebraically for the moment. And then I'm going to assume that A hat has eigenvalues lambda 1 hat, lambda 2 hat, so on. So hats will go together, things without hats go together. The key piece here, same for the eigenvectors. So v1 through vn are eigenvectors of A, v1 hat through v hat n are eigenvectors of A hat. Okay? At least the first eigenvector here is uniquely defined because lambda 1 is strictly bigger than lambda 2. Okay? Others, there could be a lot of invariances in them, so on, but v1 and v1 hat are well defined. Okay? Now, under some mild assumptions, so I can associate things, what we would like to understand over the course of this talk is how the eigenvectors of A, specifically v1, and the eigenvectors of v1 hat differ, but not in the most common way people look at this. We're going to ask the question of how do v1 and v1 hat differ in the infinity norm? So I'm actually interested in entry-wise differences between these two vectors, right? So the infinity norm is the max absolute entry. So I'm saying, let's take the vector v1 and the vector v1 hat, subject to some choice of sign. How close are they entry-wise? And I would like to understand and control this. Okay? And so this is sort of a very concrete linear algebra problem. The way I'm actually going to talk about it, got one slide ahead of myself. Okay, so why would we be interested in doing this? Well, the key is that in many applications there could be a big difference between v1 hat being v1 plus a vector that is 1 in the first entry and everywhere else, versus v1 hat being v1 plus 1 over root n, and then 1's everywhere, okay? In this case, v1 hat looks like v1, lightly perturbed in every entry, okay? Here, v1 hat looks like v1, where I've massively changed the first entry, okay? Both of these perturbations have norm 1, to norm 1, okay? Pretend I've normalized the associated eigenvectors. But here, you might imagine there's a big difference in these two cases, right? One changes the first entry a lot, the other changes all the entries a little bit. Okay? So another way to state my question from earlier is when do we get kind of well-distributed perturbations to the eigenvectors? All right? When do I sort of change them in every entry, but no single entry changes too much? Okay, so that's one question we're going to ask. The other question is that I actually care about this for a lot more than just single eigenvectors. I care about it for whole sets of eigenvectors, for the subspace spanned by sets of eigenvectors. So I actually care about this for invariant subspaces. And so the first thing I have to do is tell you what the generalization is of this question of are V1 and V1 hat close to subspaces, okay? Because I have to be a little careful about some of those statements, all right? So in order to do that, I'm going to introduce a norm that, if you're familiar with induced matrix norms, is one of those, but it's not one of the ones we typically see in, a numerical linear algebra or linear algebra class. All right, and that's the so-called 2 to infinity norm. And while it is an induced matrix norm, it actually has a very nice definition in terms of the entries of a matrix. And that is, if I ask about the 2 infinity norm of a matrix A, what I actually do is I compute the 2 norm of every row of A, and then just take the maximum over this, okay? So it's a little different than the matrix infinity norm, where I would compute sort of the 1 norm of all the rows of A and then take the maximum over it, all right? Here I actually take the 2 norm of the rows of A, and that's important for some stuff later on and how we want to think about things, all right? So this is a little bit of a generalization of that infinity norm, or the appropriate generalization for subspaces, okay? I can view this a little bit as if I ask the question of, I take the Frobenius norm of A and I want to know how well distributed it is over the rows of A. Because I could compare the 2 infinity norm to the Frobenius norm and see what that ratio looks like. An important point, and part of what makes this fun and interesting and technically exciting, is that this norm has some nice properties, but not all of the ones we would like. In particular, if I multiply my matrix A by an orthogonal matrix from the right, this norm doesn't change. Because I just rotate every row, the 2 norms of the rows stay the same. But it's not unitarily invariant from the left. It's invariant under signed permutations from the left, but not unitarily invariant, okay? And it does satisfy some nice submultiplicative relationships with the 2 norm and the infinity. So if I have a product AB, I can pull 2 norms out of the right. So AB to infinity is less than A to infinity B2, or I can pull infinity norms out the left, okay? And these come from looking at this as an induced matrix norm, all right? Okay, so with that bit of notation, let's look at the slightly expanded version of today's talk, or the technical thing I'm interested in, which is, now let's say that I have a matrix A, and I split its spectrum into 2 pieces. A part I care about, which is going to be lambda 1, and a part I don't care about, which is lambda 2, okay? And I'm going to assume that lambda 1 contains the first k eigenvalues of A, so lambda 1 to lambda k, and lambda 2 has everything else in it. Right? Little technical detail, it's important to actually put all the 0 eigenvalues in lambda 2 for some statements I'll make later. So if A is singular, if it has 0 eigenvalues, they have to show up in lambda 2. Okay?
Yeah, so you're choosing the k largest eigenvalues, or are they?
K algebraically largest.
Okay.
That's important because, well, maybe I'll say that more. Magnitude orderings are slightly more sensitive to noise than algebraic orderings.
What's the normalization on V?
V has orthonormal columns. Okay? And now I have the same thing for A hat. And throughout this talk, I'm going to assume that the perturbation is small enough so I don't have to worry about associating V1 hat and V1, that they actually go together. I can't make the noise big enough or the error big enough to just like flip eigenvectors so that all of a sudden V1 hat associates to V2 exactly or something like that. So I'm just going to assume the noise is small. Okay? So then some questions we can ask are the following, generalizations of what we said earlier, which is, maybe I want to characterize how small the minimum over orthogonal matrices is of V1 hat Q minus V1 in this 2 infinity norm. Okay? So this says, well, there's many ways to describe an invariant subspace. So instead of a plus minus sign, I have to put in an arbitrary orthogonal matrix. But how small is that quantity? Similarly, I might ask how small that quantity is for some fixed matrix Q tilde. Okay? I'm not going to talk about this much in this version of the talk, but there's a specific matrix we can put there and still try to control this. Another question is, when is that 2 infinity norm much, much less than, say, or even just less than the Frobenius norm there? Okay? Because I might expect it can actually be quite a bit smaller in terms of that. All right. So let me very briefly, for the sake of time, mention some of the reasons I'm interested in this. This is going to be a let's go with highly, or like, 10,000 foot view of some of these applications, but I'll say a thing or two, where this matters and why such bounds might be helpful, okay? And in order to do that, I'm gonna put perhaps the most simplified or a high-level view of spectral algorithms. As I said, there are a highly stylized view of spectral algorithms on the slide, and talk just a little about it. So one way to view a spectral algorithm, by no means the only way, or does this cover all of them, is that I may have some problem of interest, okay? And from that problem of interest, I end up with a matrix. That can be from any number of ways. I can be discretizing a set of physical equations, it can come from data, come from a lot of places. And then, because of questions I'm interested in for the problem of interest, I want to compute some eigenvectors of the matrix A. Or maybe singular vectors or so on, but I, for some reason, believe that the eigenvectors of the matrix associated with my problem contain valuable information about the question I want to answer. Okay? So, we compute some eigenvectors of the matrix A, or related matrices. Okay? And then we interpret or post-process those eigenvectors in some way to say something about our problem of interest. Okay? One example of this is spectral clustering for Communica detection. So some of you might be familiar with this. I have a graph. I write down a matrix associated with it, an adjacency matrix or a symmetrically normalized Laplacian matrix. I compute some eigenvectors, and I can use those to find clusters in the graph. Okay? In that world, every row of an eigenvector, every entry of an eigenvector, row if I look at an eigenvector matrix, is associated with a single node of the graph. And so if I want to think about errors in something like how the eigenvectors embed the nodes of the graph, it makes a lot of sense to think about it row-wise or entry-wise. Because I would like to know, okay, if I didn't get A exactly right for some reason, how much can sort of each node move, or each node's embedding move when I'm trying to answer this problem, not what's the worst case error I can apply to a single node, or a single node's embedding. Okay? So, actually, maybe for the sake of time, I'll do this quick and see some pictures. One example post-processing algorithm, one that some of you have seen me talk a little bit about before, is encapsulated in the following, which is I can think about for many of these problems, a reasonable paradigm is that I may compute the eigenvectors of my matrix, and let's say that's some tall, thin matrix V that has orthonormal columns, and I'm interested in finding a sparse basis for that subspace. So we have algorithms that, given a matrix V, sometimes it's plausible to compute a Q such that V times Q is sparse, or approximately sparse, okay? Or if I'm in a physics problem, spatially localized, right? But to analyze these kind of algorithms, it's important to have control over, okay, if I now change the matrix so V is not quite right, and still want to know if this algorithm works, it behooves me to understand how the eigenvectors change, okay? Because it's a valuable piece of this analysis. I'm not going to go into any of that here, but you might imagine if we have an algorithm that does this, it's valuable to understand how the eigenvectors change subject to notice. Okay? So I'm actually just going to go to this example of that. Here's one version of that, which is this from some physics problems, a highly stylized 1D1 and a 3D1, which is the eigenvectors of my matrix have corresponding points in space. They look like functions that are sort of supported everywhere, okay? Here it's a bunch of eigenvectors of a very simple model problem. Here it's actually on some molecule, but they're supported everywhere. We can compute an alternative basis where every function is highly localized in space, okay? If I want to analyze this algorithm, it's useful to have the kind of perturbation theory I'm talking about. So I guess like 2-3 minutes, yeah. All right, so let's go back to the subspace perturbation so I can show you a result or two, okay? So it turns out the dominant sort of suite of existing work in this space is primarily concerned with categorizing the distance between V1 and V1 hat defined as follows. I take V1, I form the spectral projector onto it, and I take V1 hat and do the same thing, and I look at how different they are in the two. Okay? This is related to the actual value of the solution to this optimization problem, which we know how to solve explicitly, the so-called orthogonal Prokrusty's problem. So that's what I had on there earlier. And there's a couple different ways to state this. The sort of canonical result in this space is known as the Davis-Kahan theorem, which says that, okay, some technical condition on the error, then the distance between subspaces behaves like the norm of the error, the norm of the perturbation E, divided by some gap in the eigenvalues. Okay? There's a few different specific ways to state this, but this is one. And the key piece to get at here is that this distance depends on the two norm of E. Okay? So that's a kind of classical thing. there's some related work in this area. Let's look at kind of what are the things we're looking at. So I'm going to simplify the problem a little more. I'm going to assume A is just rank K. Okay? Then it turns out you can actually build upper bounds for this quantity that incorporate some interesting information. Okay? And just to kind of highlight what this looks like, I'm going to ignore this for a second. So we saw in the other bound that if I looked at this notion of distance between subspaces, it depended on the 2 norm of E. Okay? What we notice now is that in this first term, we have something that I could upper bound with the 2 norm of E. I could also maybe control it even better. But importantly, I get a term that says if the eigenvectors themselves have this kind of well-distributed property, I gain that constant in my bound. Okay? So if the 2 infinity norm of the eigenvector itself is small, I pick up that piece in my bound here. All right? So that's actually nice. It's also even faster than Davis-Kahan because I have a square here. So faster if I think of E as going to 0. All right? I'm not going to, these second 2 pieces are a little harder to control, but you can for certain assumptions on randomness of E or so on. Okay? All right, so I'll give one synthetic example to say that we have these bounds and they work, and then conclude. So the synthetic example is we basically take a matrix A that is rank 1, or rank 1 plus a small piece we're not going to care about, and we add random noise to this. And when E is a Gaussian random matrix, we can predict the quantities of our upper bound or bound them with high probability. Okay? So we do an experiment and say, well, do our upper bounds predict these differences in subspace distance? Okay? And it turns out that, for example, if A is low rank, we can run this experiment for different rates at which the norm of E goes to 0 and say, well, okay, this first thing is what Davis-Kahan should control, and it's well controlled by what we expect. It sort of converges at the right rate as n goes to infinity. Similarly, if we look at the quantity we care about, which is this 2 infinity norm, and bound it, this comes from our upper bound, we get control over how it behaves. And it's a faster rate than what Davis-Kahan says, right? So it's not that the lines have the same slope, they're just shifted. It's actually going to 0 in a meaningfully faster way. All right? Okay, so with that, I'll go to conclusions, which is that what we have here are sort of new deterministic row-wise invariant subspace bounds that require minimal assumptions. And one of the things I particularly like about them is, I skipped over this slide, but a lot of related work in this area sort of entangles probabilistic analysis with these upper bounds. Our bounds are entirely deterministic, but you can then insert the probability and say, now can I control this under certain assumptions on the matrix E or so on in a relatively straightforward way. It's extensible to Schur form in the SVD with a few minor details being worked out. And if you want to hear more about this in more detail, I will probably be giving a scan seminar on this sometime this year. So I'll use this as an advertising pitch. For that, I'll use it as a more general pitch to say that we run a scan seminar on Mondays, Scientific Computing and Numerics. Some of you may be interested in that as well. So with that, I will conclude. Thank you. I don't know what you...
Questions?
Okay. I wasn't sure if you wanted
We'll
to.
take one question. Well, they do.
On slide 16, you've got this term E2, E21. What is
Yeah,
that?
oh, I'm sorry, yeah. These are, like, this is the projection of E onto V2 and V1. So this is V2 transpose E V1. Sorry. Yeah, that's, these slides get on a slightly longer talk, and 1 or 2 pieces of notation got lost. My apologies.
Are there other norms with applications that might be of interest and have some other subspace perturbation apart from 2 norm or 2 infinity?
So for any norm that is unitarily invariant in the appropriate way, left and right unitarily invariant, the same machinery that gives you Davis-Kahan gives you the related bound in that norm. In terms of other norms that are not unitarily invariant in left and right, all of this work gives you infinity norm bounds to within constants that only depend on the k, the subspace size, not n dimension you care about. But that's just because I can use 2-to-1 norm equivalents in a k-dimensional space instead of an n-dimensional space. I don't have anything else off the top of my head on that. I will just say this to infinity norm actually corresponds to entry-wise bounds on the difference in spectral projectors. So that's one reason this is interesting. And that if you have this to infinity control, instead of 2 norm bounds on spectral projectors, I get entry-wise bounds. So, yeah. Cool. Great, thank you.
All right. Well, thanks. Thank you everyone for coming to this presentation. First of all, let me mention that this is going to be very different from previous presentation. I pretty much removed all the technical details. So sort of the title of the talk is misleading. At the time that I was writing the abstract, I thought that I'm going to explain all the details of the work, but then realized that 15 minutes or 20 minutes is not going to be sufficient to go over all the details. So what I'm going to be talking about is mostly a big picture of what my lab is all about, what are the type of problems that you're trying to solve, and what is the motivation behind it. And I'm going to spend maybe one slide on the actual inherent parallel linear solvers, okay? And this is really a motivation for you to come and talk to me. I'm happy to tell you more in one-on-one meetings about what's really the main idea behind these inherent parallel linear solvers. So broadly speaking, my research group is at the intersection of three areas. Most of the tools that you're developing falls under computational physics. So this is really the daily work, and the type of problems that you're dealing with are coming from fluid mechanics. And the motivation comes from coming up with better treatment methods or improving problems that are related to cardiovascular disease. And I probably don't need to spend quite a bit of time explaining why we want to solve those type of problems, given the fact that out of 4 people who are dying, one of them is dying because of the cardiovascular disease, and you're spending about over $100 billion annually to basically come up with better treatment methods, so on and so forth. So I think the motivation is clear, and maybe the question that you may ask is that what the person in engineering college is going to do about it, given the fact that you have this paradigm. If you go back in history, the way that we have been trying to come up with better treatment methods was through this paradigm that you take a collection of patients and you design a control group, so on and so forth, and you study the outcome, you change a variable, and you see what treatment method works better. And there is a good reason for that, because you're dealing with the human circuitry system that is a quite complex system. But now, in the past decade or so, you have seen this growth in computational power, and also the type of method that you're using they have become more sophisticated. So you're able to simulate some of the problems that formerly were intractable. Now you're able to simulate them and basically try to understand them better. So there are a number of examples. I'm showing you 3 or 4 of those specific areas. So trying to do CFD in order to predict what's going to be the outcome of the operation, that's an example. Also, when you're designing medical devices, you're trying to understand what is going to be the failure mode of those devices, or what is contributing to, for example, in this case, long-term success of that particular operation. Or in case of diagnostic methods, can we come up with alternative techniques in order to reduce the complications associated with those diagnostic methods? And also in better understanding of some of the complications. Some patients develop, let's say, aneurysm, or either in the brain or in the abdominal aorta, and you're basically trying to use the information from fluid mechanics in order to understand those complications better. So one specific area that I wanted to mention that is related to the project that I will advertise is gets connected to the concept of customization, treatment customization. And the idea here is that if you come up with a solution, that's not going to fit everyone, right? So individual patients are different. And the idea here is that can we tailor these solutions to individual patients? And really to achieve that, what you want to do is to complete this loop, so which involves multiple components. And my group is specifically focusing on this component, running simulations more efficiently. I'm going to give you a couple of examples why that's an important component in this loop, which is, if you consider this example that, when you want to operate on a patient, recently we have developed these techniques, and when I say we, as a community, so it's a different group at Georgia Tech that has developed this technique that you could basically take, virtually modify an operation before actually stepping to the operating room and figure out what is, for example, the best geometry or how we should implement that particular operation. So, but what is lacking here is the analysis component. So this is just geometric manipulation. And what we're thinking to do is to actually add that. So basically what we're envisioning in the long term is that as the surgeon, for example, is manipulating that geometry, can we also at the same time extract what's going to be the actual outcome of the operation in terms of, let's say, in this case, the flow split between different lungs, or, for example, energy efficiency, so on and so forth. So at this point, you may realize that in order to achieve that, you have to be able to run simulations much, much faster than what we can afford at the present day, right? So each simulation right now takes several hours, and in order to be able to have real-time data, you have to be able to run these simulations in a matter of seconds, right? So you see the huge gap to get there. And I'm going to tell you about what we are currently doing in order to address this challenge, but one of them gets tied to this project that I wanted to advertise. So that's one area. Another area of where faster simulations are going to be extremely important is in optimization. So this is a single ventricle that you're undergoing an operation, and what they need to do is to basically construct a vessel between two, between the pulmonary artery and the aorta. So the question here is that what should the size of that vessel be introduced? What should be, where you should connect it, at what angle you should connect it, so on and so forth. And in order to answer that question, you have to run hundreds of simulations. And based on typical calculation costs, that's going to take months or weeks to complete, which is not something that you would be able to afford. So again, you need much faster simulations in this case. I'm not going to go over the details of that, but again, uncertainty quantification is another area. We are not sure about what should be exactly the geometry that you're constructing. We are not certain neither about the boundary conditions. So another area is reverse problems. So typically what you measure are, let's say, the flow or pressure in certain regions of the circulatory system, but what you need to specify to do these calculations are basically the model components. So basically you're trying to calculate the model component based on the outcome of a simulation, which is a reverse problem, which again requires intensive calculation. And this whole thing gets tied to this idea of infinitely parallel linear solvers. I don't have much time. How much time do I have? 7 minutes. Okay, great. So I can tell you a little bit about what this idea is. So if you think about the methods that you could adopt in order to reduce the cost of a calculation, so either you're going to be using some lower fidelity methods. Right? So think about running direct numerical simulations versus like some sort of lower order method like LES or RANS. But those come at a cost of lower accuracy. Another alternative is to come up with more efficient methods. Let's say I come up with better linear solver or some sort of preconditioner that is going to reduce the cost. We do exploit those whenever we can. So a third avenue for improving or getting to the solution faster is through parallelization, right? So the concept is that I have this problem that I want to solve, and I'm going to break it into smaller pieces, and I'm going to give that each of those pieces to individual processing unit in order to get the solution faster, right? But the problem here is that as you increase the number of processors, you don't necessarily reach solution proportional to that increased number of processors. Right? Think about it this way, that let's say you have a project that you have to do, and if you give it to one person, it might finish it in 10 hours. But if you give the same project to 10 people, I mean, they have to communicate with each other and they have to figure out the solution. So the total time that it's going to take for them to complete that project is going to be way more than 10 man hours. So you can think about if you ask 1,000 people, you're not going to necessarily finish the project in a shorter time. And the way that you can think about it in this case is that you're going to have some boundaries at the partitions that where you have to do calculation repeatedly, right? In order to make the solutions, in order to make sure that the solution is consistent. So for a typical problem, I basically plotted the number of repeated calculation as the number of processors, right? So number of processor means basically the number of partitions. And you can see for a typical problem, as you hit something like 1,000 processor, you're basically doing 40% of the work just to repeat the same calculations on multiple processors, right? And the reason that this is happening is that typically what you have is a mathematician who designs an algorithm, and he hands over the algorithm to a computer scientist who takes it and parallels it, right? So these are treated as separate problems, right? So never, with the current paradigm, people do not exploit these repeated calculations, right? So what we are thinking is that can we exploit that extra computations in order to build more efficient techniques, okay? So I didn't include any technical details, but in the past we've shown that on a related problem that if you do exploit these coupled calculations, you can actually build much more efficient techniques that is going to save you the time that it takes for you to get to the solution, okay? So and it would be great if some of you are interested, come and talk to me, so I'll be happy to tell you more about it. With that, I'll take any questions.
So for personalizing the surgical procedures, do you have enough data, patient-specific data?
That's a good question. So it depends on the complication that you're talking about. So let's say for one specific groups of patients that I've been working with in the past are congenital heart disease. So what you do know is typically a CT scan, right? So that tells you something about the geometry of your circulatory system. You may have some measurements of, let's say, blood saturations or pressure in different vessels, so on and so forth. So some of those problems that I've mentioned is basically synthesizing those information, right, in order to construct a model that is also tailored to that particular patient.
So you're solving inverse problems to deduce parts of the geometry?
So for the geometry, no, but for the boundary condition, yes. So let's suppose that we know the flow rate that is going to my hand, right? But what I need for me to be able to simulate the flow, I need the resistance, right? And that's basically the parameter that goes into my model in order to predict the flow that goes to my hand, right? So that's basically a reverse problem. So the current procedure to do that is basically a person that sits here and gets data and hand-tune it in order to get the result, right? But you can think about that process to be fairly subjective. So if you want to, let's say, come up with a better treatment method for a large group of patients, it depends on the person who is doing that, right? So what you're trying to do here is to automate that procedure, right? So that's one of the goals. I feel that I had to at least include one equation. Sorry about that.
You can write one on the board.
Yes.
So you mentioned exascale computing there, and the number of processors goes up to about 1,000. Is there a big challenge in going from closing that
Oh
gap?
yes, absolutely. Yeah. So something that I forgot to mention is that the end application of these algorithms is not going to be necessarily those that I've talked about. I mean, it's much broader than that, right? So the type of models that we're dealing with are, let's say we have a mesh that has 1 million or several million elements, right? So in that case, you don't want to go beyond 1,000 processors. But then there are problems in CFD, at least that I'm aware of, that the number of elements or unknowns in your problem are order of a billion. In those cases, you want to go to a million processor or something like that, right? And the next step in high performance computing is to even solve larger problems, right? So on there, this becomes a critical issue. How can you make sure that your applications are scaling to exascale, right? So these are the next generations of supercomputers that are coming along, right? So once you solve this problem, you could also think about, whether you could apply this type of techniques to those type of applications as well. Any other question? All right. Thank you very much.